Right, so this is going to be a sequence of short videos on ionic bonding. I'm making this for a student, but I will also make it publicly available anyway. Um, First thing we need to understand, in fact, we may involve covalent bonding here as well, but okay, so the first thing I want to understand is the electronic structure and how that relates to the periodic table. So if you imagine drawing some electron shells like we've done here, and we look at this periodic table, we can see that because the atomic number tells you the number of protons, and a neutral atom would have the same number of protons as electrons. So for now, we can say the atomic number tells us the number of electrons. It's not really true to say that. I don't like to say that sentence because if you took away an electron, the atomic number remains the same because technically it really is the number of protons. However, if we're talking about just neutral atoms, we can imagine it tells us the number of electrons because it does indirectly. So hydrogen atom has one proton, therefore it has one electron, and the first shell can hold up to two, so it would only need one shell, and the one shell is the outer shell, so it's got one electron in that outer shell, and helium has got two, and it's full. Once you've gone past hydrogen and helium, you're onto the next shell, and surprise, surprise, you're also onto the next row of the periodic table. Lithium has got three protons, which means it's got three electrons. It can only have two in the first shell, so it needs a second shell, and it's on the second row or the second period. So we can see now that the period is what tells you the number of shells that an element has. And it's in group 1. And what about the outer shell? The outer shell has one electron in it because it filled up the previous one, and now it has one electron in it, the same as the one above it, which is hydrogen, which should technically be drawn here. Beryllium, 4, still two shells because the second shell can hold up to 8, and it's got two in the outer shell this time because it's got two in the first and two in the second, and it's in group 2. So the group tells you the number of electrons in the outer shell, and the period tells you the number of shells it has in total. You can draw these like I've drawn for lithium here, two in the first and one in the second, or you can actually write them out like this. So hydrogen is 1, helium is 2. It's fairly straightforward electronic structure configuration, and this is how you would draw them for some of the other ones. And if you went down to sodium, you can see sodium is 2 and then 8 and then 1. And just by looking at this, without having to draw all the shells, we can see it's got 3 shells. It's got 1 in the outside shell. Potassium has got 4 shells. It's got 1 in the outer shell. Okay. So what about so how does this relate to ionic bonding? Well, first of all, an ion is let's look at this phosphorus atom randomly. This has got the phosphorus atom has got 15 protons, and this has currently got 15 electrons, so it's a standard neutral atom. If I were to take one of these electrons, I think I might have said the wrong word there, 15 electrons and 15 protons. So if I take one of these electrons away, it now has an excess number of protons. You can see down, this is the way I've demonstrated it below. So I'll just move this out of the way here. Let me just make sure I've got this right. Oh, I think yes. Okay. So is this phosphorus? Hang on a second. Okay, I think that might have been. In fact, I think that was chlorine I was doing there. So this is a neutral phosphorus atom. We've just I've just laid out the protons as well, back to in little groups that are representing the shells. So 2 in the first shell, 8 in the second shell, and the third shell can have up to 8, but it currently has 5 in it because phosphorus has 5 protons by definition. By the way, if it didn't have 5 protons, it wouldn't be phosphorus. So if so if I were to take away, at the moment you can see the electrons are cancelling out the protons, so we've got a 0 charge. If I were to take one away, like I've done, let's take it from here as well, you can see that now we have an excess positive charge. And if I were to add an electron, let's just duplicate that one. you can see, and duplicate the diagram down here, we can see now we have an excess negative charge. So remember, electrons are negative. So when I add electrons, it makes it negative. When I take away electrons, it makes it positive. Often a little bit confusing because the idea of taking something away and making it positive and adding something to make it negative, but it's because electrons have a negative charge. So now the thing is, those examples of what I've just done there with phosphorus wouldn't really happen because atoms want to have a full outer shell. So phosphorus is not a great example. I just picked it randomly because I had it there. But let's look at chlorine instead. So I'm going to get rid of that. I'll explain what that means in a moment. So that's chlorine at the moment. I haven't bothered drawing the protons, but it's got an atomic number of 17, isn't it? Yes, 17. Nice little trick, by the way. Think about it: the first and the second shell add up to 10. So it gives you a little shortcut to be able to work things out a little bit more quickly. If it's 17, then it's just 287 because the first shell add up to 10. First two shells add up to 10. So, as I said, the atoms like to have a full outer shell. So, in actual fact, I would, if this was going to form an ion, it wouldn't form, for example, a C plus ion naturally. It would form a Cl minus ion by completing its outer shell. Now, I did that as a little circle, didn't I? And the reason for that is because I want to show that that it came from somewhere else. So it's not one of chlorine's normal electrons. It's something else. It collected it from somewhere else, which we'll understand in a moment. So that's and also, by the way, with chlorine and with, in fact, all non-metals, all non-metal atoms, we have definitely most non-metal atoms, when they form ions, they change the name to chloride, for example, or oxide. So let's look at oxygen then. So as you can see, it's an oxide ion. Why did it form this this O2 minus ion? Because, again, just like chloride or chlorine, it wanted to form a full outer shell. So it gained 2 electrons, completing the outer shell, because it had 6 in the outer shell previously, and now it's got 8. But this means it will have an excess charge, as you can see here. So it's going to be O2 minus. So that's an oxide ion. Now you'll notice that if we look at the periodic table, that the non-metals tend to be on the right-hand side. Well, they are on the right-hand side, and the metals are on the left-hand side. And we know also that the group number tells you the number of electrons in the outer shell. So that means that a low group number means there's a low number of electrons in the outer shell, and that's on the left. So that means metals tend to have a low number of electrons in the outer shell, and non-metals tend to have a high number of electrons in the outer shell. By the way, this weird group here, 0, does that have 0 electrons in the outer shell? No, it has a full outer shell. Okay, so it doesn't need. I suppose you could say it needs to lose 0 electrons in order to form a full outer shell. Whereas this could lose 7, but it doesn't lose 7 because it's much easier for it to gain 1 in the case of fluorine and chlorine. If you go over to group 1 and group 2, so like some of the metals, then what happens instead of losing electrons, instead of gaining electrons, they actually lose them. So lithium, as you can see up here, if we wanted to make lithium a full outer shell, then rather than giving it 7 more electrons, it's a lot easier for it to take away 1. And this is going to be the case with all metal atoms. In fact, basically, that's kind of the definition of what a metal atom or what a metal is. Metals lose electrons when they form ions, and non-metals gain electrons when they form ions. So that would mean that lithium would form a positive ion. In fact, all metals form a positive ion. So So if I did make a lithium ion, it would be Li plus, and we learned earlier on that chloride forms a Cl minus ion. So if we had chloride, if I had a lithium ion like this, Li plus, and these don't change their name, by the way. They're just called lithium ion. Let's put that in a. Let's shrink that and put that into a little circle. Yeah, and I'll put that inside there. And I'll just zoom in a little bit because I want to make a few copies of this, and I'll make this circle red, and then this circle can represent my lithium ion. And we'll do a similar thing with our chloride ion. We'll make it blue. I tend to do negatives as blue and positives as red. I think that's what many textbooks will do as well. Let's copy that and make it blue. Okay. Oop. Okay then. So there's my chloride ion. I'll group that, and let's group that as well. Now of course, we have a negative charge and a positive charge that are going to be attracted to each other. What would happen if another chloride ion comes along? Well, it would still be attracted to this positive lithium ion, wouldn't it? And likewise, if I had another lithium ion, well, it would be attracted to this chloride ion like that, and you'd end up this kind of going on and on, and you might form a sort of pattern. It won't necessarily be quite so straightforward as we're seeing here, like just a crisscross sort of chessboard pattern. But as far as what you need to know, you can imagine that they all form this pattern. They don't in reality, but what you do need to know is that they form a pattern, and this sort of, it's called a lattice. So that's not quite right, is it? We need to add a layer. I know what I'll do. I'll delete that one. So this is made out of ions, as you can see. So it's an ionic lattice. And what we've done here is this is an ionic bond an ionic lattice is comprised of ionic bonds. Now this is different to covalent bonds, which we will look at, in that these lattices, sort of by definition, that's kind of what a lattice means, is that there's no real end to it. I could always make it bigger and so on. It also means it's because this strong attraction between positive and negative bond, it's got a very strong force, and so it's very difficult to break it up, and in other words, to melt that solid that I've just drawn there. Okay, so it has a high melting point, and for the same reason, it has a high boiling point as well. So ionic substances have a high boiling point and a high melting point. What else did we notice about that? Well, we have it donated and it received electrons. This non-metal ion became an ion by receiving or accepting an electron from the metal atom, and the metal atom donated the atom. So the the electron. So in in ionic bonding, they receive and donate electrons. Now, what I haven't drawn yet is how to include these diagrams in an ionic. How do I demonstrate an ionic bond with these diagrams? I've nearly done it, and let's imagine we zoomed in all the way into this diagram. We try to work out what's going on with the actual electrons. We already know that the chloride ion is going to look like that, and the lithium ion, well, I haven't quite drawn it, have I? But we know that the lithium ion will look like this, but without that electron there and without that shell. So we know that the lithium ion is positive. We know the chloride ion is negative. What we tend to do is draw square brackets around. I say tend to. We do draw square brackets around it. It's just a convention. And then we draw a plus sign like that. And then we draw one there. And do a negative symbol there. So that's my ionic bond. And the thing to realise about this as well, I'll tell you what, I'm going to... No, never mind. I was going to make this positive. I can make that just that red. Like that. And maybe make this one blue. So the other thing you can do, by the way, with these is you don't actually have to draw the other shells. You only have to draw the shell that has been affected. And so with the lithium ion, we can actually get away with just doing that. And with the chloride ion, we can get away with just doing the outer shell. Like this. Oops. There you go. So that's how you draw them, how you draw an ionic bond. What about this oxygen here then? Let's imagine I was making lithium oxide. Well, that's my oxide ion. This is my lithium ion. Remember, actually, I don't need to draw this middle shell here, this first shell here. Oops. Only I need to draw the square brackets. I'll put that again. So that's 2 minus. Now there's a problem here, as you can see, because the charges don't balance, and also this lithium can't have given both of those electrons. So what must have happened is that another lithium ion gave the other electrons, and so you have the formula for lithium chloride would have been LiCl, whereas the formula of lithium oxide would be Li2O. Now, we're going to look at covalent bonding in a moment, but it's important to realize here that these are not molecules, as I demonstrated up here. They form lattices. So there'd be another this isn't how you would draw it, but technically there'd be another one over here like that next to it, but that's not how you draw it. This is how you draw the actual bond, but it can lead to some confusion because people imagine them to be like molecules of lithium chloride and molecules of lithium oxide. There's no such thing as a molecule of lithium chloride or a molecule of lithium oxide, because you cannot have an ionic molecule. Ionic substances do not form molecules, they form lattices. And so really, when I put Li2O or LiCl, what I'm actually saying is the ratio of lithium ions to chloride ions. So if I took a load of lithium chloride, like the one above, I'm saying there's a 1-to-1 ratio of the ions, whereas if I took a load of lithium oxide, then within that structure, within that lithium oxide, there's a 2-to-1 ratio of lithium and oxygen. So I think maybe we can just finish by looking at these questions. I should have said at the beginning that to feel free to obviously pause it, rewind it. You should do this with everything you study from anyway. But yeah, but as I'm going through this, but maybe we can do a little check here and pause the video now and try to fill in those gaps or work out what those gaps would be. Okay, so let's have a look. An ion is an atom or... I didn't explain this bit, sorry. It's a molecule. So a molecule that has an... I don't know. I'm guessing it might mean excess. Either has an excess, either protons or electrons, or has, and maybe if it didn't have an, I'd say has a charge, either positive or negative. So I don't think that's a very good one. An iron is an atom or molecule that has a charge, either positive or negative. Cations, didn't teach you that word. Cations have they have less. So a cation is called a cation because it goes towards the cathode. I didn't teach you some of this terminology, did I? So sorry about that. But it goes towards the cathode, which is the negative electrode. The reason why it goes towards the negative electrode is because it's positively charged. So it's a little bit confusing because despite the fact it's got CAT at the beginning, which you normally associate with negative charge, it is in fact positively charged. And so cations have less electrons, so have a positive charge. Anions have more electrons, so have a negative charge. So anions would go towards the cathode, anions go towards the anode because they're negatively charged, and anodes are positive charge. And cations go towards the cathode because cathodes are negatively charged and cations are positively charged. Every atom and ion wants to gain that's probably going to be full outer shell, as this makes them more stable and less likely to react, I'm guessing. They do this, I'm not sure what that word is. Sorry, I've given you rubbish questions here. Less likely to, who knows what, I don't know. But certainly gain a full outer shell. Full outer shells work out the ion that would form from this is a better question. Work out the ion that would form from if these elements have a full outer shell. Well, we did oxygen is O2 minus, we already did that. You can kind of work this out by looking at the periodic table. Oxygen's in group 6, and so it's got 6 in the outer shell, so if you gave it 2 more it would be full, so therefore it needs to gain 2 more. That'll make it an O2 minus ion, and remember it's a non-metal, so we know it forms a negative ion. Magnesium is in group 2, so it's going to lose those 2 electrons to form a full outer shell because it's easier to do so. Metals form positive ions. So that's going to be Mg2 plus. Nitrogen is in group 5. It's a non-metal ion, and so it's going to gain 3 electrons to form a full outer shell, and that'll make it 3 minus. Remember, electrons are negative. Neon, neon is a noble gas, so work out the ion that would form. So that's probably a trick question. Neon doesn't form ions. I mean, as I say, you can technically make any of these things ions by just taking away electrons in theory or giving it electrons, but naturally the most likely thing is that they would attempt to form full outer shells. So okay, so that's basically ionic bonding. So I'll stop that video and then I'll make a little video about covalent bonding.